Good morning, everybody. Hope you enjoyed last evening in Lugano. Nice weather. Today is action time and hands-on. So the whole day, the plan is the whole day is to go with exercises and hands-on. But if you also want to test other things, you're welcome to do it and ask us, and we're here to help you with that. So until lunch, or let's see, I mean, we can shift the times, it doesn't matter. Mondays will start and we'll show you, you will do some basic hands-on on the basic directive, the data management, the loops, everything. So it's good that you get from the GitHub that I showed you yesterday. There is a repo.txt file in your home where you can get, where is the link to the repo, then you can clone it. And yeah, this is how to follow. I have put up the slides, all the slides from yesterday. It's there on. And yeah, we're here to help you. And the next, and after lunch, we're going to do 2 more exercises that they combine also MPI and CUDA. So you can see and you can play a bit with the interoperability between CUDA and OpenACC and how you have an MPI code with OpenACC.
So yeah, good morning everybody. I would like to ask you to really copy that repository, since the exercise I want to do it with you together, it's real. I mean, I really want to do it with you together. So you should do all these small steps. I want to present them here also. I want also to present my results I got when I did these examples, but I would like you to also do that and to compare if you get the same result and if you get to the same conclusions and ideas to go further and further to port this really simple and small code. So did every one of you got already the repository? Who did not got that already? You need help with that? So in the meanwhile, I would like to give you some short overview what this exercise is about. So this simple example, I would like to guide you through a simple porting, or a porting of a simple code, let's say it like that way. It's a real simple application. There's no MPI included and no advanced stuff, so that we will do later, but just to get in touch with OpenMP, OpenACC in the first place. The Himeno benchmark, which I used for that example, is a 19-point stencil calculation. So we do an update of a cell using neighboring cells in each direction. And the code is provided in 2 versions. So there's a Fortran and the C version. There's no C++ version. You will see if you go in the directory, there is the basic code. And we want to modify that one then afterwards. The code itself, it's around 230 lines. Yeah, and it's just statically allocated arrays. Why I use this simple example, we really want to focus on how to port the code to OpenMP. We do not want to have any issues about not understanding the code. So really, I think when porting a code to the GPU, we really have to get an idea of what the data structure is, how the call tree is, how the data is passed through the call tree, and so on. And that's why I use this simple example. Yeah, while working with that simple example, I will also ask you to use all these tools I presented yesterday. So the compiler feedback, the runtime commentary, and also the profiler. And what we have to deal within this whole session is how the data is passed through the whole call tree. I mean, we will do that in the second next step. And in the first step, we mainly have to focus where are our hotspots. So where we have to concentrate in the first place when porting our code. And then we will see we have to deal with minimizing data movements and stuff like that. So, as mentioned in the first place, we really have to understand our application. If we are not the original developer of the code, we have to get in touch with that. We have to find out, okay, what's the application is doing, where the most time is spent in the application, and so on. So that's what we do in the first place. Then we need to implement the first OpenMP kernel. We check the performance afterwards, and then we also will check how much data is passed, how often, and so on. So that will be then the next step to introduce also data region and then maybe move them up the tree, and maybe if we are successfully supported the code, then we will be able to really port more or less the whole code on the GPU. So yeah, let's get in touch with the code, do an initial run on a CPU just without any OpenMP, without any parallelization. And therefore I would like to ask you, so give me a second. There's the screen. Never did it like that way, but so I would like to ask you, in the repository, so the OpenACC training directory, there's a subfolder exercises with a subfolder Cray, with a subfolder Himeno. There you can select the C or Fortran version. I myself will go with the Fortran version. I already compiled yesterday, so I have some more files hanging around. But you can just do a kind of make. Okay, I did already the make. I can do a make clean make. All right. Yes?
The assumption that you're using the Cray compiler?
I do, but you could also try with another compiler if you want. I mean, if we want to get compiler feedback, you can also do it with different compiler. I think I already included compiler feedback also for PGI.
So compiles
Yes.
with PGI without acceleration.
Yes,
I'll
that's
try with PGI.
with PGI. There's also compiler feedback enabled then. Sure.
So, where is name? Oh, it's job name. Okay.
Excuse me. Yeah, I corrected that yesterday. I don't know. In the repository, it's corrected already.
I will correct it and then they can put it. I did some corrections
Okay.
yesterday.
So there was an issue, or there is an issue in the job script.
And it will run, but
No, it was complaining for me yesterday. I forgot that. In the second line for the job name, I think it was written there just name, and the workload manager is complaining about that, so you have to correct that to -- job name, or pull it from the repository and then it's corrected. So when you compile it, you could just run it if you want. I would also suggest to do a module load perf tool space and also perf tools. I would now just go for perf tools light loops directly, and then I recompile, and therewith I already instrument the code with profiling. And then to submit, I just do an sbatch submit.wlm. So, any issues with that? So if you have questions, raise your hand. We are here to help you and answer questions. That's why we are doing that workshop. So who of you got already a result, performance, and output? Excuse me? What do you mean with 2.5 minutes left? Okay. So then, if it's successfully run through in the output, you should see different values, and beside of the runtime, you should also see estimated performance in megaflop. And then there's also, we call it here GOSA, so that's a checksum. There's my mouth. A checksum called GOSA, and that's what we will use to verify if our code is still correct while porting our code. Yes?
I've just fixed the scripts, the submission script, this problem with job name. So if you pull and you haven't changed your submission script yet, you can just issue git pull origin master and you will get the updated version.
No, the submission script is the submit.wlm. So let's see. Yeah, maybe we should also mention that one, but most of you already ran on the Daint system, right? So you should be all familiar with submitting a job, monitoring if the job run, so on.
Just if you want to see the status of your jobs only, so there is the command SQ, and then you pass the -u option and then your username. So then it will list only your jobs, and you will not get lost into thousands of jobs that are actually running on Piz Daint. Yeah, the username is course 0 whatever. And by SQ, I mean S and Q the whole word, not just the letter. Just to, because it sounds the same, but it's not. There was a misunderstanding about the reservations and stuff. So you have to source a script. So I thought it was in your .bus.rc. So JD now will show you how to do that.
if you don't set those variables, you have to give all the arguments to the srun command line. So to make your life a little bit more simple, you should set those variables. So either in your bash RC or which I did here because that's my bash RC, so I just put that. Or you could also source
that one. Yes.
that file. If you source that file, then it will set the variables, and then you can just do srun your executable.
So you need to source the file in OpenACC training exercise tools, the course SH, or you can source that one and then maybe also copy the free variables into your bash RC, then the next time you do not have to source it anymore. The exercise, since the exercises have almost no output, you could run it from home. In principle, I would suggest to run your application from scratch, at least if they have significant output. You could run that from home. No question?
I still don't see anybody having submitted a job at the reservation, so have you managed? Yeah, but okay.
That's great, right?
You have sourced
We don't need GPU.
Okay.
Actually, it's a very, very simple example and small one.
For us, it worked without sourcing it. Why is that?
Okay, great. So, who of you already got some output? Yeah, okay. Excuse me? Yeah, I can show you. So, the output should look like that one. At the beginning I just copied the submission script into the output file. Then we should see at least that output here, which is the actual application output. So the whole stencil calculation ran several iterations, and that 2 times. So there's just 3 iterations at the beginning, just as a kind of initialization, and then 1,000 iterations for the actual measurement. And then we have the runtime here, the GOSA, so the checksum of the application, and the...
You don't see anything that you
Excuse me?
Yeah.
You were trying to show something with the mouse, but you don't see.
Oh, since that is smaller than my screen here. Okay, I also have to change that one. Give me a second. Apply. So if I mark it here, all right, I cannot mark it here. That's the bad thing. I can mark it here. So let's see. So, okay, I have to turn around. I don't like that, but it's the only way to do it. So the runtime, right? Then it goes at the checksum we have here, and then the megaflops, which is an estimated value we have here. GOSA is the checksum. So we do a checksum of our matrix, and then we have to compare that one with the next runs to see if, the stencil calculation, if there change anything in the stencil calculation, the GOSA changes, and then we know something is wrong with our code.
What is the stencil calculation?
Okay, so right. So the stencil calculation is that you do an. Where is it?
You just want to have this number stay the same.
Right. And we calculate the stencil, so we do an update on each cell of our 3D grid, and the update is that we do a calculation with all the cells around, so with all the nearest neighbors, calculating an update to the actual point. And if this calculation changes somehow, we break something in our computation. So we want to stay in this GOSA, the checksum, to be the same.
So for 3 and 100 iterations, they have different figures, is it normal or not?
Since this is a different iteration cycle, right? If you change the grid sizes, we can also do that. The GOSA will also change. But for staying with the same grid and the same amount of iterations, the GOSA should stay the same.
I see. So for the different number of iterations, it can be different.
Yes. Oh, no, I wanted to stay here. Forgot that. So, why? I don't see that here. Oh, because I'm on the wrong presentation. Right. So, hopefully all of you got some results now. A time you agree with my runtime, almost same, similar?
Fortran is a little bit faster.
Yeah, that's fine. You also got similar GOSA, right? Same size. So then you could also compare with my slides then later on. And what else would I want to mention? I mentioned that one with the GOSA. So we compared it. Who of you did already the profiling one? I did that. So then I would like to ask you, excuse me. Yes. So who of you did it? Loop profiling with CryPad? No. So I would like to ask you in the next step to get an idea where the most time is spent with our application. We do profiling. So please do module load, perf tool space, module load, perf tools base, and perf tools light loops. Right? In my case, it conflicts because I already loaded it. And then just make clean, make, and rerun your application. So I give you some seconds for that. Should I need to go back or? No. So as a result, what we should see is then below our actual application output, we should see the CryPad performance statistics. And there, why it's different than my screen? Okay. So there on the top we see some general overview of our application. So we see that that the number of MPI ranks is 1. We also see how many process elements per node are used, how many cores per socket the CPU itself has. We also see when the application was run. This is quite nice to compare different applications. So if you go step by step, you can nicely follow in your development process. You also see where on which system your application ran, and also the processor speed and CPU information and so on. Then in the next, the application process time and also a memory overview is printed. And then below that, in the first table, we see an overview of our main computation functions. So in the first column, we see the relative computation. No, it's not the computation time. It's it's computation time. Since we do tracing experiments, so we really measure the time of each function and also here of each loop within the function. Then we see the real time, so in the first column the relative time, in the second column the absolute time. We also see the time for the loop, the amount of iterations the loop is processed, the average trip counts of the loop, and then minimum and maximum trip count. And then in the last column we see which function this loop is, and we see also on which line here. We just see it too, but if you see it in your output, you see it's the first one is on line 268, right? So, excuse me? Loop trips means how many times the loops is iterated. So how many cycles the loops is performed. So the trips, the loop hits is the amount of how many times you reach the loop, and the trips are how many times you cycle the loop. Sure.
So I was looking at the reservation and there were no jobs, and then I realized that for some reason the variables do not work. So I've just updated the scripts with options that you have to pass. So it's you can just git pull origin master, or in your job scripts you should add 2 lines. One line should be, can I show? If you just yeah, can I? Can I pull here? You are the positive.
Yes, you have to exit via them.
Oh, okay.
It's English. Excuse me.
It's English.
It's English.
Okay. So if I do origin master. Okay. So now I have the updated.
Submit.
Yes.
Now we have the updated submit script. Oh, we don't have that. Maybe there's a conflict since I changed also the submit myself.
But they didn't get. Oh.
Since I updated that one.
Okay, can I
Yes.
So you see there, you have just to open those last 2 lines. So SBATS reservation equals open and SBATS account equals courses. So then everything will be submitted in the reservation. Otherwise, you have to pass every time those 2 options when you invoke the SBATS command or the srun command. No, it's not necessary. It's the default partition. But if you like, you can put it.
So I need to put it in the script or into this?
It's the same thing. If you put it in the script, it's not necessary every time to pass the option, unless you run with srun directly. If you run with srun directly, you have to pass all the options.
But if I have it in my buffer C, then
No, I've just tested that, and I don't know why it doesn't work now. So,
Anyways, who of you did already the profiling? Okay. Who of you already had a look in the code on the most time-consuming line? None of you? Okay. So let's do that. Let's have a look what's happening on that line. Oh, I forgot. Which line number was it?
Actually, why is the two times are different? The relative, which one should I look at?
What do you mean? So the...
Tell me the most favorable.
You mean the first and the second column?
The second and third, so there are two different times, which
So the first one is the percentage of the overall runtime. So that's, let's say that's 99.6% of our, where's my mouse now? Of our 35 seconds, right?
and the other phones, how are they different?
And the
So I guess the second is probably really the time in seconds, and the next one is some adjusted time.
right, and I think that's the one included in the loop. I mean, if you have the first line, right, that's the most outer loops, including the second line. You can nicely see that also from the loop hits and trip counts. So you hit that twice, you have 500 trip counts here. The next time you hit that 1,000 times, right? So that's 2 times these 500. So you have a double nested loops, and in the third one, it's again the triple nested one, and that's then the most inner nested loops, which then spans the whole time. So the time within these 3 loops itself, within the loop without the inner loop, is quite small. So the most time is spent within these loops. I mean, there are some instructions done in the outer region not containing that loop. You know what I mean? So you have a certain loop. Maybe I can draw that small picture. So let's say you have your for loop I equals 1 to something, and then you have your for loop j equals 1 to something, and then you do maybe some computation there, and you have your for loop k 1 to something, and then spend some time here. That's the most time we see here, that's 29 seconds, and there's some time also spent for this computation there, which is then presented here as the time for each loop in the third column. Okay? So let's have a look to line 268 and especially to 277. the Himeno version 00 dot, in my case, F90.
I have like x and then x plus another and then x plus something. So this one?
So there are the Himeno underscore, the language you use, C or Fortran underscore, the version tag I used, dot, the ending for the. And you already see you have some more files hanging around, like these. I have to show it here. So there's also a ZG file, which is compiler feedback quite close to the assembly. So if you really, really want to know what the compiler is doing, you can have a look to that. Then there is also the up file, which is after the compiler feedback after the optimization, which is better readable, let's say, more easy readable than the ZG file. And then there's also the Himeno listing file. We will have a look to that one later, which is the one I showed you yesterday in the presentation. And now I want to have a look to the actual source file. In my case, it's the F90 file. So then this should be 268 in my case. So this is the most outer loop we saw, where the overall most time is spent, and then we have the 3 times nested loop here with our actual kernel. So there's our kernel computation updating the matrix to the SO and SS elements, right? And there the most time is spent, so we can also have a look to the compiler feedback, what he is already doing with the CPU version. So we can do in VI listing file, excuse me?
Some compiler intermediate representation of the code in the CG.
In the CG, right, that's what I mean. But first I would like to have a look to the listing file. So at the top of the listing file, we have a short summary, which compiler we used, in which version, which target is used, what are the compiler options used. So you see all the libraries which were linked, which source file it is, also other options which were used for compiling. Then you have a short legend for all the annotations which are used. So as mentioned yesterday, for later porting, where we are interested is in the capital G for the accelerated one. Then there's also the small g for the partitioned one. Interesting is also if it's blocked. Then what for optimization is also very interesting, which part of our code is vectorizing. And then there are other things like pattern matching, unrolling, inlining and stuff like that. And then we can go down the code, and we were interested in line 268, 77, something like that. So we see here, oh, it's different. So we see here, we have a triple nested loops. That's why there is 1, 2, 3 at the beginning. Then we see it is vectorized, and it's 3 times unrolled. And we also see we have these 2 pluses here around the loops, and therefore we can go down and see on line 268 the most outer loop was not vectorized because it contains a call to a subroutine. The same for the next inner loop and the one, and we see the most inner loop on line 277. This loop was vectorized. This is at least a good sign for the pure CPU version. That's maybe also the reason why it's so fast. But we want to get it even faster while porting it to the GPU. What did I miss here? Ah, I changed the German layout. So, presentation. So, checksum, we did that. Okay. So what you could also do is getting a real overview about your application. For that simple application, it's quite easy. If you have a real complex application with many source code files, it's very difficult to get the overview about the whole application. But here I just want to show you what the application does. So we have an initialization at the beginning. Then we call this Jacobi routine with 3 iterations, and we get back the GOSA. We measure the time around that one, and then after some computation output, we do that again in the initial case, for 1,000 iterations, and then we do the computation of that, and at the end we print out our timings. So within this Jacobi routine, which was called 2 times, we have an iteration loop here at the beginning. So this is the most outer loop. And this contains 3 triple nested loops here for each dimension, and doing there the stencil update. This is what I meant here. And then at the end, the temporarily variable, we call that work2 here, is copied back to the original pointer. So the stencil we saw already, so this is an update about forward nearest and backward nearest neighbor. We also calculate the GOSA, I described it already. Compiler feedback, I already did that, so you will get the slides. You can have a closer look if you're more interested in details on slides. So now we want to introduce our first kernel, and I would suggest to afterwards comparing different versions to really do inversioning. So what I would suggest is just copying the source code file to a different file name. You could also use a source code repository like Git, but it would be maybe too difficult for now. So yeah, copy the file. If you name it like 01, so use the same naming like me, then you just can use the make file to compile the different version easily. And then, yeah, what to do? How to introduce the first kernel? Who has an idea?
Add annotations.
What we have to write then, where?
Take the heaviest loop, for example. Take this loop, the 3 views, and at the beginning put the annotation. But I don't know. Somehow I would like this annotation to be applied to all 3 loops.
That's a good point. So he mentioned that we have to put some annotations he mentioned, so our directives around these loops here, and he mentioned also it should apply for all 3 loops, and it will do. That's
something like collapse 3, like OpenMP work.
Okay, you mentioned we should use a collapse 3. We can try that later. That's a good suggestion, a good idea. I will mention that tomorrow in more detail, how we can do the loop scheduling manually or suggest the compiler maybe better ways to do. But anyways, if we add our target directive on top of the first loop, it will handle all 3 loops and distribute them in a certain manner. So you have to introduce our first kernels around these 3 times nested loops, which span the whole computation, which should, I mean, that's the goal, that we have a lot of trip counts within these loops to have a lot of work for our huge amount of parallelization. And the target teams distribute then tells the compiler with the target directive to offload our work. The teams means that we want to spawn the thread blocks, and the distribute means that we want to distribute our loop work into these teams.
So I guess in C it will run OMP.
Right.
And the rest is the same.
Except that in Fortran you also have to use the end statement in C. You can neglect it. Yes, the rest is the same. And then what we also have to use is the reduction variable, since Goza is a sum here of all elements of our loops. So when we go through our loops, we sum each element to Goza, right? To get that sum by all of our threads correct, we need to reduce Goza by applying reduction variable on it. Excuse me? Okay, I can explain again. So this Goza variable here sums the product of SS for each element of our loops. Since we distribute now the loop cycles to the threads on our GPU, right? So we have different threads treating different loop iterations. And at the end, we want to sum these value Goza of all our threads. We have to tell the compiler to do that. So merging the values of all of our threads into one value. Goza here. If not, if we would not do the reduction variable, each thread would calculate one Goza, right? But then just the latest one would commit that back to our CPU, so we just get one value from one thread, which thread ever that would be. Okay? So then?
Is anybody else using the C version? Because in C the syntax should be a bit different. I guess we need the backslash as the continuation line.
Right, excuse me. Continuation is different.
So there should be a reduction plus Goza 1 should not have separate OMP.
Okay, wait, I can also show that to you. Need a second.
If you just put in the same line, then yeah, and you just need the continuation character. So in C it would be OMP target teams distribute reduction all in the same line. I think it should work.
Backslash? Oh, I can put it on the same line.
Yeah.
Yeah, you can write it in the same line. I just did it here on my slides and in the code, just, you know, to stay within the slides.
I think this is special Fortran continuation stuff. So in C you just put the backslash and the line goes to the next. So.
Oh, I am very sorry. I even do not have that on the slides from yesterday.
I guess if you put
Exactly.
it might be not accepted, or it's not accepted in some cases.
No, you have to do it. Yeah, it depends. I mean, if you say, for example, a parallelization pragma and the data pragma, that's fine. And then for completeness, we could also do our data clauses here. So we could also specify that I, J, K, S0, and SS are private variable, but actually that's not necessary in that case since the compiler would do it anyways. Yes. Right.
How is doing this better than doing a parallel OMP parallel do?
The OpenMP parallel do will parallelize that for the CPU. If you want to do it on the GPU, you have to use that directive.
So, okay, just so I understand.
Wait.
Oh.
The one that has the microphone, so he's talking.
I have the magic wand. Okay, just so I understand. Basically, we're vectorizing such that the index k, because it's outside the largest loop.
Right.
So that k is being spread over the different cores. So each core is taking a different value of k.
How that will be distributed on the GPU, we will have a look in a second, okay?
Okay, yeah. All right.
So get that done first, and I would like to go on. But when you compile, have a look in the listing file, there we will see it. You can already do that. So do when you already add the directives, do make clean, make. I should mention it. So you do in, excuse me? No, this is just one call here, right? So we have the line continuation, so this is just one call. And you have just to close it once. You can also break it up maybe and have two calls, then you have to close two, right? But in that case, it's just one. So, no question?
So I can also write this in one line. That's
Yes, you can also write it in one line.
And now it's applied only to the outmost loop. So
no, it's applied to all three of them. Since it's nested loops and OpenMP realized that it works on all three of them.
Okay. Thank you.
But you could also
Yeah.
do it for every loop. You could also do that for every loop separately, right? Then you would need three.
You could also specify, if you have a certain loop length and you know the compiler is distributed it in a non-optimal way, you can also specify it in a different way. So that you say, okay, I want that this loop is distributed in that way, but we will talk about that tomorrow, okay? That's more advanced. But yes, you can do that.
But perhaps the question was that could you add OMP target teams for every, in front of every of these three loops? Perhaps no.
Like distributed loops.
Because you should get in then just one kernel.
Wouldn't make sense though.
It wouldn't make sense, no, to add the target teams distribute in front of each loop, since that anyways acts on all three of them.
Okay.
But so you say OMP realizes there are nested loops, but would it also work if the first loop starts and there is a lot of code, and then later the nested loop starts with a lot of code?
Yeah, and most time you could check that with the compiler feedback. I want to do that in a second.
Oh, so it will really look for.
But I guess the loops should be perfectly nested.
What do they really have?
Yeah, I mean, that's the best case if the loops are perfectly nested, yes. I mean, depends on the compiler how intelligent it is and realize that, yes. So let's have a look to the compiler feedback. I have to jump here, so do a make clean. Yeah, so for that version, you also have to load the module. Don't want to do that on the module, CRAP, SL, NVIDIA 60, since we want to go to the GPU now.
Just a quick reminder, make sure that you have put the ---- reservation and ---- account in your BUD script before you submit for this version. in the submit WLM.
Or just pull.
Yeah. But if you pull, you should make sure that it updates it. Because if you get an error, then you have to step back and...
So, to compile the new version, I add the flag for the makefile. You can just add the version equals the number you selected. So in my case, it's 01. And now we want to use OpenMP, so we also have to specify OpenMP, yes. You can also change that within your makefile if you want, but that's the way I do. And then this creates a new binary called Himeno something version 01.x, which you also have to change in your submit script to then run that executable. But this will be the second next step. In the first step, I would like to check what the compiler is doing. So having a short look again in the listing file of our new source code. Okay, excuse me, that one. So if you have a look on the listing file, you should see same or similar things like me. Hopefully not. Hopefully you see the accelerated version. All right. Do you see? Yeah. Great. I did something wrong. And I can guess what. Yes, I didn't do that.
Just a note, what Mandas just did with a module load Cray PE Excel NVIDIA is very important if you compile with a Cray compiler, because then it loads the target architecture, so the compiler will understand the OpenMP4 and OpenACC directives, and it will generate code for the GPUs. If you don't do that, you will get into this problem that Mandas just showcased.
Yeah, then it's just compiling for the pure CPU version, yeah. Right? And
so make sure that the Cray PE Excel NVIDIA 60 is loaded.
And we also have to say on PES.
Yes, the OMPS is specific to the test case here, to the hands-on example. They
So, yeah, I want to go back. So, if you have a look to the listing files, and I messed up my makefile, I guess. So it was not using OpenMP in my case. Correct it in a second. But in your case, hopefully, you will see that it's accelerating. So you should see these capital G here for the whole region of your OpenMP region. And then you should also see the small g for the partition, so for the inner loops. And then we can also get more details if we go down at the end of the function. And there we have several lines. I just printed a few of them here. And there we can see how it is distributed. So we can see, okay, the loop or the loops are placed, I mean the kernel is placed on the accelerator. Then we see that the most outer loops should be partitioned across the thread blocks. And we should also see that the inner loop, so the I loop, should be partitioned across 180 threads within these thread blocks. So you see the middle loops is executed redundantly within the thread blocks, and the most inner loops is then partitioned within the thread blocks with 128 threads.
What is the joint GB represented?
Excuse me?
There is GB and then GB.
So the capital G means that it's accelerated. The small g means that it's partitioned. The B means that it's blocked. This is for memory handling. And then it's again partitioned, since the inner loop is also partitioned. This is the, where's my mouse now? This one, again partitioned and again blocked. So you have, if you have multiple nested loops, it acts on each loop, and then you have multiple time blocking and partitioning.
Does it signify something if it is attached together, the G and B?
Excuse me?
Just the G and B are together, and they are not just before that. So I was just trying to understand if.
You mean because it's no space in between?
No space. Does that mean something?
No, I don't think that it's meaning something.
Okay.
That's just kind of a typo. Yeah. There are two more questions.
So it seems like in this output we are seeing that all loops were partitioned, accelerated, also nested loops. But I still am wondering if I had some code before the second nested loop starts, would it also realize and do that or not? What you were talking about perfectly nested loops, does it mean they have to be like 4, 4, 4?
You can have some statements in there. It should recognize then also the nested loops, but I think it depends on how much you have in between and what statements there are. I mean, here you also see that, for example, the second nested loops, it's working redundantly on that. So, I mean, it's always selecting the most efficient way from the compiler point of view. So here also the second loop is just, treated like a loop, work redundantly, and just the most inner loop is partitioned across the threads. So this is up to the compiler. If you, as a programmer, have the opinion that there's a better way to do and you want to optimize that, you can act on that. You can then really say, okay, I want that loop partition, and you can also say, okay, I want partitioned in a certain way with certain amount of thread blocks with threads and so on, but that we will fit tomorrow.
Okay, thank you.
what does it mean? So that loop at 277
Excuse me?
the loop starting at 277 is partitioned across the 128 threads within a thread block. Oh, sorry, in your case.
So here my last line?
In your case, 272. Sorry, I'm reading off my screen. So I also have a comment which says a loop starting, in your case, at line 271 was not partitioned because a better candidate was found at line 272.
Yeah, since
what does that mean?
OpenMP usually just do 2 levels of parallelization. So we act on thread blocks and threads. So we have threads within thread blocks, but we have kind of 2 levels, right? So it's acting, it's taking the most outer and the most inner loops to partition these ones. So the most inner loops spawns the threads, and the most outer loops is partitioned on the different thread blocks. So it's kind of similar as you think that the most outer loops is partitioned to the SM, so the symmetric multiprocessor, thank you. And the most inner loops then spreads across the threads within these.
Okay, so it's because it found an inner loop that was more inner than the first inner loop.
A better candidate for these kind of.
And so presumably, if there had been a fourth loop,
it could also act on that one.
It would have ignored the middle 2.
Yes, maybe. Maybe the compiler also realizes that the fourth loop is maybe just with 2 or 3 trip counts, and then working on that redundantly and taking the most outer one.
Okay, all right, thanks.
Now a question? Excuse me? So I would suggest let it run and see if you still get the correct results. And in the next step, I would also ask you to swap the perf tool light loops module to the perf tool light GPU one. Right? Since we have now a GPU version, we want also to monitor what's going on with our application on the GPU, especially with data movement. And in the meantime, I could check what I'm doing wrong.
Cling. It is copying data, spends a lot of time for that, and that actually kills all the benefits of GPU.
Give me 1 second, please. It was a good point. You should repeat that with the microphone in a second.
There is no microphone.
Well, now the program spends most of the time copying data between host and device, which kills all the benefits of using GPU. Actually, we already put also initialization part to GPU2. This didn't change much. There is still some copying taking place.
Good point. So could you also explain how you find that out?
Well, there is the output of the profiling, and it lists time which is spent at different stages. And the very first stage is copy, and copy takes more than 70% of all the execution time, on the host, of course. Strange enough that the listing refers to the line number where the call to Jacobi function stays, which is not very informative.
Excuse me? It refers to the line where the
for
OpenMP
this
directive is.
For this copy operation, it refers to the line where the Jacobi function is called.
Ah, right. Okay. Yeah.
So actually, we don't see exactly the place when the copy happens. So perhaps it's not very important.
So, in the first place, I would check that we still get the same results. You should also do that. So in my case, I get different about, what's that, 10 to the minus 9, which is quite accurate, I would say. Yeah, the performance decreases more or less drastically. So we will fix that. But we have to find out why. So we can also see the data movement which is planned in the listing files there. But I wanted to show you also that one, right? So if we go to the, why can it go up here? So in the profiling, we see that, as he mentioned, almost 80% of the runtime is spent in copy operations of the to the accelerator and back. We also see here how much data is copied. So it's 45,000 megabytes. You cannot see it here, so it's copying in, and copy out, it's 4,000 megabytes. So why is that much data copied? Yes? Excuse me? For me, it's only 6 seconds, yes?
No, 6 seconds is on the, or 5 seconds here is on the accelerator. And on the host, we have 52 in the version.
On the host, we had 52. Let's see again. The
no.
original.
I'm mistaken.
There's my log. There's my log. So in the original version, we had 35 seconds in my case. Average process time. And now we have 6 seconds. So anyways, we want to see what's happening, and therefore we can, on the one hand, I can also do that live here with the screen. So we go again back to the listing files. No. And now also my one should be correct. So also in my case now it's accelerated. And then down here, it is also mentioned which data is copied to and back to the accelerator. So we see here P, A, B, C, and so on. They are all copied to the CPU and back. So that's what the compiler is doing. But now, I myself would also like to know what's happening during runtime, and therefore we can set the environment variable, for example, cray ACC debug, you can see it, equals 2 in our submit script, right? You could also try it with the NVIDIA profiler using the compute profiles equals 1. You should see similar things. And then I just resubmit my batch script. Excuse me?
Which option was it exported? Which environment variable?
Excuse me, that in the batch script I already prepared. On the one hand, you could do it with the cray runtime commentary, cray ACC debug equals 2, or you use it with the compute profile equals 1. That's the NVIDIA one. You're welcome. I didn't change the name. So you already did that? So fast, my job finished already. Maybe I give you a second. So I now enable the runtime commentary with the cray ACC debug variable setting by 2, and then we should see how data is moved forth and back to the GPU. And, excuse me?
Where did you change?
In my submission script, there is a, cannot see the top.
It's flag, right, somewhere?
It's a variable, environment variable called cray ACC debug, and I set it to 2.
So is the cray ACC debug only going to work with the cray compiler?
No, I think it also works with our compilers. You compile with PGI? Then you can try.
But all other things that we're doing, do they work with other compilers?
The compiler feedback is a, I mean, with that option I used, it's cray specific. Other compilers can also do compiler feedback, like I showed you yesterday, PGI has the minfo flag.
So you mean LST file?
Yeah, right. I mean, there it's not the LST file, it's different, but yes, similar output.
But the performance information?
You mean profiling, craypad? Yeah. That you can do with any compiler, at least with that one. If you want to do it with the loop profiling, it's, I think that one is just working with cray compiler. If you want to use it with reveal, and therefore you need to create this program library, this is just working with the cray compiler. But a general profile you can do also with GNU, Intel, and PGI. So who of you already got this runtime commentary? Are there any issues, questions?
What should we be looking at?
What we should looking at? Yeah, that's a good question. So I would, in the first stage, get an overview. So let's go step by step maybe first to get an impression.
I'm interrupting in the heat of the moment. I know that you all want to continue, but it's coffee break. If you like.
Coffee break. So
it's already
everyone
10:30.
can get close to. So I ask you, who did not got that runtime commentary? Get that, and the one who got that already can go for coffee. No, just joking. We can all have the coffee break now.